So here are the solutions for D2 stellar characteristics and evolution. But most of this is repeats from D1. So 8A is a new question that we haven't seen yet. So we're going to do 8 and 10. Those are not repeats from D1. Just as D1 had a ton of D2 content in it, looks like D2 has a lot of D1 content in it that we already saw in those solutions, so no point in doing them twice. All right, so let's take a look at 8A. All right, so we have two graphs here. One is of intensity versus wavelength, the observed spectrum from a star of intensity versus wavelength. Notice there are dips in that graph, right? And then we have a reference intensity versus wavelength for the hydrogen emission spectrum. And then 8A says, why is star X likely to be a main sequence star? Well, the hydrogen emission spectrum is a clue, and main sequence stars, before they get old and start running out of hydrogen to fuse, main sequence stars are mostly hydrogen. And it's like, all right, well, what about this star though? What about star X? How can we tell that it's main sequence, or how can we tell that it has hydrogen? So there's two different spectra here. The reference spectrum is the hydrogen emission spectrum. That's for that's again an emission. It says it right there, emission spectrum. But the observed spectrum of a star is an absorption spectrum. So rather than the gas emitting frequencies, it's going to show the emissions of all frequencies with some wavelengths that are absorbed. And so those are the dips, the intensity dips that we see. We see four of them, 1, 2, 3, 4, four dips corresponding to 410 nanometers, 430 nanometers, 490 nanometers, and 650 nanometers, which is pretty close to what the hydrogen emission spectrum is showing. So what this absorption spectra shows for certain is that hydrogen is definitely prevalent in this star. So yeah, main sequence stars have mostly hydrogen, and the absorption spectrum of the star confirms the presence of hydrogen. And then maybe it's only 2 marks, but I should probably say why. So yeah, the absorption spectrum of the star confirms the presence of hydrogen because the absorption wavelengths match the emission spectrum of hydrogen. 8b says show that the temperature is approximately 10,000 Kelvin, so we would use for that lambda max times the temperature is 2.9 times 10 to the negative 3 meters Kelvin. So we look for the maximum wavelength that comes in at right there. And if we go down to the bottom here, we get that the max wavelength seems to be about 280 or maybe even 290 nanometers. And so we get temperature is the 2.9 times 10 to the negative 3 meters Kelvin over the maximum wavelength. That gets us 10,000 Kelvin. All right, so we have ourselves a graph here. This looks like it is a logarithmic plot. It is logarithmic both in the x-axis and also in the y-axis. And so we have luminosity versus temperature. Looks like following diagram shows the main sequence. Yes, this is an HR diagram. So we know that this star X is main sequence, and we know that its temperature is 10,000 Kelvin. So then we find it on the main sequence. 10,000 Kelvin, here's our line right there. So if we go across, that gets us right around here on luminosity. And again, the way these log scales work, you can see that the lines kind of get smaller as it goes from 10 to 100, but they work, it's the same, it's like counting by 10. So we have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And so based on, let's see, the main sequence looks like it is hitting, oh, hold on a second. I could be a little bit more precise here. Let me fix that. There's 10,000 Kelvin, so we find right around there. So the closest line I would say is this line here. Let's see where that goes. And so we go across and we see that it hits about 40 according to what I'm seeing here. Let me add in 30 here, 30. This is 20. So it's saying 40 in terms of the solar luminosity. So I would say it comes in as 40 of the luminosity of the sun. And the mark scheme says 35 plus or minus 5 for that based on the graph. And then 8D says what's the radius of star X in terms of the radius of the sun. And so we have a ratio, luminosity of X to the luminosity of the sun. The constants cancel out. Talking about spheres here, so the area of a sphere is 4 pi r squared. And the 4 pi cancels out. Maybe I think I didn't make clear like the reason why I'm using L equals Stefan Boltzmann area T to the fourth. It's because the radius of the star is in the area formula, and it's relative to the sun, which is why I did a relative luminosity of X to the sun. And so we're trying to drill down on the radius of Rx relative to the radius of the sun. So I have Rx squared of R radius of the sun squared is luminosity of X times the temperature of the sun to the fourth over the luminosity of the sun times the temperature of star X to the fourth. And so I square root both sides to get rid of the squares on the radius. And we know the luminosity of X relative to the sun is 40. And then the temperature of the sun is given somewhere. Tricky. They actually want you to pull the temperature of the sun off the HR diagram that they gave you. So, all right. Now, a couple things. We know that Lx over Ls is 40. We got that over here. It's the relative luminosity of X, or the luminosity of star X relative to the luminosity of the sun. So we know that. And then the temperature of the sun, how do we know that that's, the mark scheme says 6,000. Where is it pulling that from? Well, the luminosity of the sun is 1. And so if we go across on the 1 line, we see that it corresponds to the main sequence on the HR diagram over here, which lands us right here in terms of temperature. And so following this log scale, starting from 10,000 to 1,000, we have 9, 8, 7, 6,000 Kelvin, 5, 4, 3, 2, 1,000 Kelvin. So that's where the 6,000 Kelvin is coming from. And the temperature of star X was given over, in one of these problems, there's the temperature of star X, 10,000 K in 8b. And so when we work that number out, we get that the radius of X relative to the sun is, and so we get a relative radius of star X relative to the sun of 2.3. Mark scheme says anywhere from 2.0 to 2.3. Alrighty then. 8e, what's the mass of X relative to the mass of the sun? So luminosity of a star is, or the relative luminosity is proportional to the relative mass raised to the 3/5. It's asking about mass. So relative mass is proportional to relative luminosity to the 1 over 3.5. And we know the relative luminosity is 40. And we get a relative mass of 2.9, which is inside the range of values. It says, do not accept mass of X is equal to 35 to the 1 over 3.5. Right, because it's really kind of like the relative mass. It's not the actual mass, so maybe that's why they said don't do that. Yeah, 2.9. So yeah, the ratio is 2.9, or we can also say that the mass of X is 2.9 the mass of the sun. That's another way of saying that. Mass of X is not literally 2.9 kilograms. That makes no sense. So yeah, it's a relative factor there. All right, so now let's take a look at 8F. All right, and then the final piece of number 8 is 8F. It says star X is likely to evolve into a stable white dwarf star Why does the radius of a white dwarf star reach a stable value? And I think for 2 marks, and I think the mark scheme explains it pretty well. The star collapses until the inward and outward forces equilibrate, they balance out. And the reason why that's true is because of the electron degeneracy pressure. The electrons get so close together that their Coulomb forces push against each other. And there's not enough mass to gravitationally crush beyond that pressure. Okay, and then 9 is another repeat. Looking for 10. All right, and so here is number 10. I have 2 stars, series A and B, binary star. Binary star is 2 stars together. This is 2 stars orbiting a common center of mass. Stars that orbit each other do not accept that. That's interesting. I've actually used that turn of phrase. What I mean by orbiting each other, I mean a common center of mass. But that's interesting that they say do not accept stars that orbit each other. They are 2 stars orbiting a common center of mass. All right, then 10b. We have a peak spectral line of 150 nanometers, shows that the temperature is 25,000 Kelvin, and so we have the equation lambda max is 2.9, lambda max times temperature is 2.9 times 10 to the negative 3 meters Kelvin. And so we have the peak wavelength, and we're looking for temperature. Don't forget, of course, that nano is 10 to the negative 9, so we're going to need to put in the 10 to the negative 9. And so when you divide that up to 2 sig figs, you get 25,000 Kelvin. So show that Sirius B is not a main sequence star. The masses are the same, but the luminosities are not. It's actually luminosity of Sirius B is 2.5% the luminosity of the sun. So this proportional expression means we're talking about relative luminosities and masses. And so it says that the masses of the two, mass of the sun over the mass of mass of Sirius B over the mass of the sun is 1. They're about the same mass. And so that's 1 to the 3.5, which is, of course, 1. But in order for, if they have the same mass, they should have the same luminosity in terms of that relationship, and they don't. So the luminosity of Sirius B is 2.5% that of the sun, and by the relationship between luminosity and mass, for a main sequence star, if their mass is the same, then their luminosity should be the same, and they are not, so therefore Sirius B does not follow the main sequence relationship and is not a main sequence star. And then 10D has one of these fun radius problems. So luminosity is definite Boltzmann area T to the 4th area of a sphere is 4 pi r cubed, and we have the relative luminosity, and the looking at Sirius B relative to the sun. Of course, our constants all cancel, and we know that the relative luminosity is 2.5% or 0.025. Temperature of Sirius B is 25,000 Kelvin. We figured that out before. And then the temperature of the sun says 5,800 Kelvin. I made a boo-boo. Area is not 4 pi r cubed, it's 4 pi r squared. Let's go fix that. And so when we work the numbers and we get the solve for the radius of Sirius B, we get 0.0085, the radius of the sun, which matches the mark scheme. It didn't match the mark scheme when I was raising the radius to the 3rd, but it's not to the 3rd, it's squared. So there you go. So 10E says identify the star type of Sirius B. All you need to do is answer it, just say white dwarf. But the reason why it's way hotter than the sun, it's 25,000 Kelvin as opposed to 5,800 Kelvin, and it's much, much smaller. 2.5 times, 2.2, I'm sorry, 2.5% the radius of the sun. So it's a compressed core of a former star. It is a white dwarf. And it's a white dwarf that is, yeah, it's off the main sequence, right? Because a white dwarf, it was once on the main sequence, I'm sure, until it became a white dwarf. All right. Then let's continue. We have ourselves an HR diagram. Okay, so Sirius A and B, A's main sequence, so its luminosity is proportional to the relative mass of the 3/5. It says that its mass, its relative mass of Sirius A relative to the sun is double. So 2 to the 3.5 is 11.3. So Sirius A has roughly 10 times the luminosity that the sun does. So being in the main sequence, being just above the luminosity of the sun, gives it that position. Sirius B is a white dwarf, so it's going to be at the lower left of the diagram. And then finally 10G, that sequence, the evolutionary path of Sirius A's main sequence star, it will go to from main sequence, it'll go up into red giant phase, luminous but cool, and then it will come around, get hotter and smaller, and wind up in the white dwarfs. And this will be true for nearly all main sequence stars. All right, that's it for D2. Thank you.